I want to talk about the math of matrices. This is a common thing that comes up in physics, and I'm going to talk today about just the very basic math that you do to manipulate matrices in much the same way you would manipulate numbers. Now, to do that, we have to talk about what matrices are, what they look like. And maybe you've seen some of this before, but I'll cover the basics. A matrix is described by the number of rows and columns that it has. So this matrix that I've called A has 2 rows and 2 columns, so I call it a 2 by 2 matrix. B is also a 2 by 2 matrix, 2 rows, 2 columns. M here has 2 rows but 3 columns, so it's 2 by 3. And V has 3 rows and just 1 column, so it's 3 by 1. We often call V a column vector for that reason, and you can probably guess what a row vector would be. So the whole point of this is that we can treat matrices a lot like numbers in a lot of ways. Other ways they're weird, but there are things we can do to treat them like numbers and do math with them in sort of standard looking math. What's that mean? So thing we might want to do in math is addition. And addition for matrices is pretty straightforward. If I want to do A plus B, I look at these two matrices. A crucial thing is for addition to work, the two matrices have to be the same size, same number of rows and columns. So same size. And if they are, all we do, we just go one by one. We say in the upper left-hand space, row 1, column 1, we just say 2 plus 4. Row 1, column 2, 1 plus 1. Row 2, column 1, 0 plus 1. Row 2, column 2, negative 3 plus 0. And so that would add up to 6, 2, 1, negative 3 as my result. And you can see the result's the same size as well. So as long as the two matrices are the same size, you can add or subtract, same deal. So this is good. By the same token, you can do equal. You can set this equal. They've got equal signs here already, showing that each individual entry is the same in each of those places. 2 plus 4 is 6. 1 plus 1 is 2. 0 plus 1 is 1. You get the idea. There's no way of making sense of addition of two matrices if they have different sizes. Nothing we can do about it. So we've got that. What else can we do with matrices? Probably the most interesting thing comes up when we multiply matrices. And matrix multiplication is a little weird. There's so many numbers there, how do we make sense of it? Here's the plan. If I want to multiply matrix M times matrix V, if I want to multiply those two together, there's going to be a procedure to use. But first I have to check. Matrix M is a 2 by 3 matrix, and matrix V is 3 by 1. And this is only going to work if these two numbers are exactly the same. If the columns of the first is equal to the rows of the second. That's when you're allowed to do matrix multiplication. The result is going to be a 2 by 1 matrix. 2, take out the 3 and the 3, by 1. That's the result. The size of the resulting matrix we're going to find. Here's the procedure that we use. We're going to go through the rows of the first matrix one at a time. Let me copy this down over here so we can see it a bit better. The rows of the first matrix, so 4, minus 1, 2, minus 5, 3, minus 2, times 1, 3, 0. So there's my product. Those are the two matrices I'm multiplying. And here's what we're going to do. We're going to start, we're going to have 2 rows in our result. For the first row of the result, we start with the first row of the first matrix. And what we do, we go with the first entry here going across. And one at a time, we multiply them by the entries of the second one going down. That's why the columns here has to equal the rows there, because each column is going to be multiplied by the corresponding row. So let's see what happens. 4 times 1, 4 times 1, plus, we add them up. This is just like a dot product of two vectors, except we do it a few times. 4 times 1 plus negative 1 times 3 plus 2 times 0. So 4 times 1 plus minus 1 times 3 plus 2 times 0 is going to be my first entry here. There's only one column over here, so we stop with that. Next, we come down here, and we do negative 5 times 1 plus 3 times 3 plus negative 2 times 0. And when I work that out, this is 4 minus 3 plus 0 is 1, and negative 5 plus 9 plus 0 is 4, and that's my answer. And you can see that I got one row for each row of the first matrix, and one column for each column of the second, so it was a 2 by 1 matrix I got in the end. That's m times v in this language. That's great, that's great. What would happen if instead I did, what else can I match up? How about this? How about A times M? A, remember, is 2 by 2, and M is 2 by 3, so it works out the way it should. These are both 2 in that place, so that's good. That means it matches where it needs to, and my result should be a 2 by 3 matrix in the end. Let's see how this works. I guess I should write out the two matrices just so I have them right here in front of me. A is 2, 1, 0, minus 3, and M, again, is 4, minus 1, 2, minus 5, 3, minus 2. And what do I get from this? I'm going to put it together. Again, what I do, I go one by one through the rows of the first one and one by one through the columns of the second one, and I multiply pairs. So I start with the first row and the first column, and I'll go 2 times 4 plus 1 times minus 5, and that's my first entry. For the next space, it's still the first row of my result, but now I'm going to the second column. I'm going to put a comma here just so I can distinguish more clearly. First row, second column, 2 times minus 1 plus 1 times 3. There's another comma just to distinguish. That was this first row in the second column. And now here, third column, 2 times 2 plus 1 times negative 2. That's going to be my entire first row written out now. And I can do the same thing for the second row. I'll get 0 times 4 plus minus 3 times minus 5. Minus 3 times minus 5. I know it's boring watching me work out math. 0 times minus 1 plus minus 3 times 3. 0 times minus 1 plus minus 3 plus 3. And finally, 0 times 2 plus minus 3 times minus 2. Plus minus 3 times minus 2. Okay, and I can work this all out now. I can work out my individual results. That's 8 minus 5 is 3. And this is negative 2 plus 3 is 1. And this is, let's see, 4 minus 2 is 2. And down here, 0 plus 15. 15, 0. Oh, that's the time. Sorry, that was supposed to be 3 times 3, of course. Negative 3 times 3, yes. So 0 plus negative 9. So negative 9. And here's 0 plus 6. So there we go. I got a result when I multiplied these two matrices together that is 2 rows and 3 columns. 2 by 3, leaving out the two things that cancel in the middle. It's notable that when I multiply by a square matrix, it doesn't change the size. The second matrix size stays the same. So that's a handy thing, that square matrices won't change the size of your matrix. All right, so I've done that. A times M. Good. We can see how matrix multiplication works, and it all seems pretty sensible. Now notice, in these cases, I could not have multiplied V times M, because that would have been 3 by 1 times 2 by 3, and the dimensions wouldn't work out. You couldn't do this thing where you go across one and down the other, across one and down the other. You couldn't do it because they don't match. I couldn't have done M times A because it wouldn't match. The one case where I can do it both ways, where I can compare both orders, is if I have 2 square matrices being multiplied together, 2 square matrices of the same dimensions. In that case, A times B, for example, A times B, what do I have? That's my 2, 1, 0, minus 3, I believe, times 4, 1, 1, 0. Let me go through and just show you what happens when we multiply these together. We can see 2 by 2 times 2 by 2 gives us the right, it matches in the middle, so we can do this procedure. I've got 2 times 4 plus 1 times 1. I'm just going to do this all in my head now that you know the method. 2 times 4 is 8 plus 1 is 9. 2 times 1 is 2 plus 0. 0 times 4 minus 3. and 0, 0, so that's 0. That's what happens when I multiply A by B. But this is the one case where we can do it in either order, right? And with ordinary numbers, we'd already know the answer. It's exactly the same. But this is one of those places where matrices and matrix math turns out to be very different than ordinary math. 4, 1, 1, 0, 2, 1, 0, minus 3. When I multiply these two together, let's go through it. Try it yourself as we go along. Let's try this out. In fact, you could pause the video. Try this and see what happens. I get 4 times 2 is 8, plus 1 times 0, so that's 8. 4 times 1 is 4, minus 3 is 1. 1 times 2 is 2, plus 0 is 2, and 1, 0, so that's going to be just 1. And notice that these are different. This is not the same as A times B. So that's a striking thing about matrix multiplication, is that even when you're allowed to do it, it doesn't behave quite the same way as ordinary number multiplication does. The technical term is that matrix multiplication is non-commutative. The order matters for matrix multiplication. So if you're in the habit of like alphabetizing your variables or something, don't do it if they're matrices. The order is really important. You get totally different results depending on which order it is, and it's really important how it goes. So okay, that's good to know. But we've got this idea about how matrix multiplication works. I guess maybe one more matrix multiplication thing to mention, and that is the idea of the identity matrix. I is the identity matrix. Identity meaning 1, meaning it's like multiplying by 1. And really it's I subscript n by n, because every identity matrix is an m by n matrix, and it is just 1s on the diagonal and 0s everywhere else. So this would be I 3 by 3. If I did that. Often we'll leave out the 3 by 3 subscript because it's obvious in context what you're multiplying by, what fits there. But yeah, this is where it's just 1s down the diagonal and 0s everywhere else. That's called the identity matrix because it turns out, let's just try it, if I do 1, 0, 0, 1 times, let's use our matrix A, 2, 1, 0, minus 3, we'll find we get, our result will be 1 times 2 is 2 plus 0, 1 times 1 is 1 plus 0, 2 times 0 plus 1 times 0 is 0, and 0 times 1 minus 3 minus 3, it's the same thing. Multiplying by the identity matrix doesn't change your matrix. So on either side, if I remember order matters, it doesn't matter for the identity matrix whether you multiply from the right or the left, it's going to give you the same matrix you started with. So that's the equivalent of multiplying by 1 in matrix language. It's the identity matrix. So that's the basics of matrix math. There's one more thing I want to bring up because it's sort of related to this, and it's an important tool to use in some other places. The other piece I want to talk about is the idea of the transpose of a matrix. And the transpose of a matrix is just what happens when we reverse the rows and the columns. So the transpose is just swap the rows and columns of your matrix. So for example, A transpose is going to be, when I read across 2, 1, that'll go down, 2, 1. And when I read across 0 minus 3, 0 minus 3 will go there. Or M transpose is going to be, when I read across, I get 4 minus 1, 2, so that becomes vertically 4 minus 1, 2. And my next row becomes my next column, minus 5, 3, minus 2, minus 5, 3, minus 2. And there's my M transpose. Notice, incidentally, that while this was still 2 by 2, because it started as 2 by 2, this one becomes 3 rows, 2 columns. This is now 3 by 2. So it's a different size. It swaps the rows and the columns. It's a different size. That's the transpose of a matrix. And the one thing I want to say here, to relate to, what do I want to put this? I'm going to leave that up for a second. To relate that to what we've done before is, notice that if I do M transpose, it's 3 by 2. I should have written this down. V transpose is going to be, what is it? It's going to be 1, that wasn't a good one, 1, 3, 0. This is 1 by 3, right? It's a row vector now instead of a column vector. That's V transpose. And here's the neat part. When I do that, M transpose V transpose, obviously I can't do M times V, or M transpose times V transpose, because it doesn't match. 3 by 2 can't multiply 1 by 3, because the 2, it doesn't match the 1. What can I do? The thing I actually can do is this. I can write down V transpose M transpose, and that would be 1, 3, 0 times this tall thing, right? 4, tall thing I said, tall. 4 minus 1, 2, minus 5, 3, minus 2. This one should work, because remember, this is 1 by 3, and this is 3 by 2. So I do match in the middle. These 3 and the 3 match up, so I know I can multiply them. And at this point, what do I get? Let me just write it down. And again, I'm not going to write down every single step, but I'll get the pieces. That's 4 minus 3 plus 0 in the first column. So 4 minus 3 plus 0 is 1. And my second column, minus 5 plus 9 plus 0 is 4. And look at that, 1, 4 compared to what we had when we multiplied in the first order. That tells me this is equal to M times V transpose. That's kind of cool that the transpose of a product is just the opposite ordered product of the transposes. That's the relationship we actually can use, and that guarantees that if the 3's lined up before, the 3's will line up again. It swaps between those two, and everything works out nicely. So those are some of the things that basic tools we use with matrix math. And maybe the one other thing to say about transpose, because it's a useful terminology, useful piece of terminology, is the idea that there are some matrices, they have to be square, that look the same whether or not you've transposed them. And we say that if A transpose equals A, well, it doesn't here, I should use a different letter. If F transpose equals F means that this is a symmetric matrix. Symmetric matrix. So for example, if I have 3 minus 1 minus 1, 7, transpose, if I swap the rows and the columns there, that gives me 3 minus 1 minus 1, 7. Cool, that's fine, that's symmetric. If F transpose, maybe I should use a different letter, a different label. If G transpose equals negative G, we often call that anti-symmetric. And anti-symmetric matrices would look something like 0, 4, 1, minus 4, 0, 3, minus 3, minus 1, minus 3, 0. This is a 3 by 3 matrix, and you can see that if I do its transpose, the transpose of that is 0, minus 4, minus 1, minus 4, minus 1, 4, 0, minus 3, and then 1, 4, wait, no, 1, 3, sorry, 1, 3, 0. Doing that transpose, when I do a row here becomes a column, row becomes a column, row becomes a column. When I do that transpose, you can see each one of the entries is the opposite of its corresponding entry in the other one. And the one thing to notice there is that means the diagonal entries of an anti-symmetric matrix all have to be 0. Because, well, they're all 0. When you swap it, the diagonal entries don't move, so there's no requirement on those. There's no limit on what those could be, except it has to be 0. It has to be equal to its own negative. So, okay, up here, I guess here is where there's no requirement at all. This could be anything, because it doesn't get changed at all, so there's no limit on what could be up there. That's pretty much everything I want to say about the core ideas of matrix math. There's some other things to talk about, but these are the basics. This is the basic idea that goes into every matrix math calculation you'll ever do. And I hope it serves you well.